Mars sample return has been a high priority for the scientific community for a long time. The dark comedy sort of joke has always been that Mars sample return is 10 to 15 years away, no matter what year it is. So here we are, we actually have a mission, it's built, it's sitting at the Cape, it's getting ready to be launched. That will be the first stage in returning samples from Mars. It's just huge. It's an Apollo 11 type mission because of the unique properties of Mars, because of the whole question of has life ever existed anywhere else? All of those things are all wrapped up into this particular mission. The question of whether any environments on Mars were habitable or are habitable today is really what drives things. There's this remarkable global climatic change that occurred right around 3.5 to 4 billion years ago on Mars that took it from a planet that probably was habitable to something that's desolate and dry and irradiated at the surface with a thin atmosphere now. The really interesting thing is to do this comparative planetary geology to say, well, why did the Earth evolve the way it did with abundant life, and why did Mars evolve the way it did in its own unique way?
To find answers to these questions, scientists use orbiters, landers, rovers, and recovered Martian rocks that can survive the trip down to Earth.
I'm sitting in the University of Alberta Meteorite Creation Facility. It's a lab that I built and designed where we have a clean room, which you can see over my shoulder here. It's the sort of glassed-in area. And the rock cabinets in there have about 1,800 specimens of different meteorites from around the world. The Martian meteorites are a unique set of rocks that have been blasted off the surface of Mars naturally. There's 140 or more meteorites, and over 80% of them are basically lava flows that flowed out on the surface of Mars in the last few 100 million years. Now, Mars is 4.5 billion years old, so there's a whole history there that's missing because of a bias in the way that these samples are delivered to us.
And that's what makes this upcoming launch an ambitious new chapter in Mars exploration. It's the first step in a series of proposed missions over the span of a decade to bring samples back with all of the source material.
The idea is to go to a place where the rocks are of that age of at least 3.5 billion years so that we can probe those for evidence for ancient life. The landing site is Jezero Crater. It's a remarkable 45 kilometer diameter crater that was filled with water, had a river flowing into it and a river flowing out of it in a key time frame in Mars's history. There are mineral signatures that have been detected from orbit, including carbonate. And carbonate is a mineral that life can sometimes use as part of producing, say, a hard shell. Those rocks are beautifully preserved. You can see them from orbit. And that's the real reason why this was chosen. The whole idea is to get a cache of samples that are so compelling to the scientific community that the space agencies could do nothing less than spend the money to basically bring everything back.
That's a tall order for this new rover, but luckily, NASA's engineering teams are experts at building capable robot geologists.
Mars 2020, the advancement is adding the sample caching system. We have a bit carousel that holds all of our various bits or tools that we have for working on Mars. We have a 5 degree of freedom robotic arm that's on the outside of the rover that allows us to not only dock for tool exchange, but also for placing some of the science instruments. The drill is able to not only be a jackhammer where it actually takes out the sample from the rock, but it's also able to do very delicate tool drop-offs. It's a very complex system.
This is the inside of Building 248 on the NASA JPL campus. It's where Eric and his team put the sample caching system to the test.
So in order to really make sure that the system's going to work, we always try to emulate the environment that we're going to work in. We have a geoanalog team that allows us to collect rocks, something approximately close to what we might see on Mars. We created this unique test setup where we're able to be in a thermal vacuum chamber that allows us to get down to the Mars pressure. We have to make sure that we've learned how to get the teeth of the drill just right to get a sample. And our testing over time has been an iterative process that helped us design a better, more reliable sampling system.
The targeted launch window for this rover is July through August 2020, with a landing date of February 2021. After it survives the trip to Mars and sticks the perilous landing, the rover will take some time to get situated.
There's usually a commissioning period. It's been a long ride and everything's just kind of unfolding and getting itself ready. At that point, they want to start taking advantage of where they're at. Where do we land? What can we see?
The main approach is to look at a region of interest, do a walkabout. We have cameras that are able to get the mineral signatures of rocks. We have the SuperCam, which is essentially a laser that can zap the rocks a few meters away and tell you what they're made of, which I just love that. It's fantastic. That one has a microphone attached to it now too, so we'll be able to hear the rocks getting zapped from a distance, which is pretty awesome. There is going to have to be a certain balance between the desire to completely explore and then decide from there what samples you're going to get.
We're trying to keep everything within a 1 Martian year, which is about 2 years Earth time, to get all the samples collected. There is a pace that the science and operations team are working to. There's 43 tubes. 37 is the number that we expect to bring back. Our job is to put a sample in every tube, and the scientists will have to choose which ones to leave behind. So we hope to give them a really tough decision.
I'm really looking forward to those conversations when we're doing the mission operations. We got a bit of a hint of it a couple months ago when we were all working remotely on a simulated rover mission where the folks from NASA JPL went out to the Nevada desert and set up a bunch of instruments and made it look like the rover was there. And the discussions about what to sample were absolutely fascinating. Something that would be really compelling would be like a mudstone, like a really fine-grained rock that was deposited within the delta that has lots of organic matter in it. Another really compelling thing, of course, would be these carbonate rocks. So this whole discussion about should you collect that particular sample, or should you explore more?
After some careful decisions, the rover will start caching.
Once we've taken a rock from the ground and it's in the tube, the sample handling arm inside the belly of the rover will actually go and pull the sample out and start to process it. The autonomy that's built into the system is fairly incredible, and there's a lot of closed-loop motor control activities. Once we actually expose a sterile tube to the Martian atmosphere, we have a 5-hour timeline to actually get it sealed. Contamination is a critical part of our mission. We don't want to take any organics with us. This is something that feels like a sci-fi movie, but it's reality. The plan is to drop off the samples in bunches around Mars, where a future mission would land and use the fetch rover to go and pick them up. They'll be installed into a Mars ascent vehicle, which will then launch off of Mars into a Martian orbit, where another mission would come rendezvous and pick up the sample. And then that orbiter will then turn back and head back towards Earth.
The current plans are for the samples to be returned to Earth in 2031. There's a small but non-zero chance that there's extant life that could come back with the samples. And so that's where the other part of Mars sample return is really important, which is the sample receiving facility. And then the design of that is going to be next level kind of stuff though, because at the same time that we're trying to keep whatever is in the samples from getting out into the Earth environment, we're also trying to keep the Earth environment from getting into the samples. I'm one of 10 people selected as a return sample scientist through a NASA call. These are all people like myself who have experience in the lab with samples of meteorites. You know, age 13, I think I said, I want to be there when the samples come back. And it's a dream come true to really be involved as a return sample scientist, as someone who is an expert in what you do with the samples when they come back. I sure hope I'll be able to see them. I'm going to have my favorites. They are going to be curated under the best possible conditions and preserved indefinitely for generations to come. Each one of those will be scrutinized like you wouldn't believe, the way that all the Pulse samples have been scrutinized for 50 or more years now, with the added bonus, of course, that we're actually going to an environment that could potentially have been habitable.
To hopefully answer the big question, was there life on Mars?
I don't really have a good answer for that, but another way to look at that question is to say, well, if we don't find life, and that's a significant step toward understanding what life is all about and how unique it is, for example, for the Earth. On the flip side, if we do find evidence for ancient microbial life, it just opens that door to life being incredibly abundant throughout the whole universe on these almost infinite number of planets that are being discovered in our galaxy and beyond.